We are covering the analysis of singly reinforced concrete beams using the Whitney Stress Block, a key topic for the FE Civil exam, found in the Civil Engineering chapter of the NCEES Reference Handbook. This method is fundamental for determining the flexural strength of a concrete beam. The actual stress distribution in the concrete's compression zone is a complex parabola. The Whitney Stress Block simplifies this into an equivalent rectangle, which makes the calculations manageable under exam time pressure. The depth of this block is denoted by A, and the uniform stress is assumed to be 0.85 times the concrete's specified compressive strength, F'(C). This simplification is an accepted ACI code method and is what you will use on the exam. It's critical not to confuse the stress block depth, A, with the neutral axis depth, C. The neutral axis is where the strain is 0. The relationship is A equals beta 1 times C, where beta 1 is a factor that depends on the concrete strength. For F'(C) up to 4,000 psi, beta 1 is 0.85. You'll find the formula for beta 1 in the handbook for higher strength concretes, but for the FE, 4,000 psi is very common. Let's walk through a typical exam problem. Imagine you're given a beam with a width B of 12 inches, an effective depth D of 20 inches, 4,000 psi concrete, and grade 60 steel, meaning Fy is 60 ksi. The tension steel area AS is 3 square inches. The first and most important step is to establish equilibrium, where the total compression force C equals the total tension force T. The tension force T is simply the area of steel times its yield strength, AS times Fy. The compression force C is the volume of the stress block, 0.85 times F'C times the depth A times the width B. A huge exam trap is units. Concrete strength is in psi, while steel strength is in ksi. Let's convert F'C to 4 ksi to be consistent. Setting C equal to T, our equation becomes 0.85 times 4 ksi times A times 12 inches equals 3 square inches times 60 ksi. Solving this gives a stress block depth A of 4.41 inches. Once you have A, you can find the nominal moment capacity, Mn. The formula is Mn equals the tension force T multiplied by the moment arm, which is the distance from the centroid of the steel to the centroid of the compression block. This distance is d minus a over 2. Plugging in our numbers, Mn equals 3 times 60 multiplied by 20 minus 4.41 over 2. This results in a nominal moment of 3,202 kip-inches. But the exam almost always asks for the design moment capacity, which is phi times Mn. The phi factor, or strength reduction factor, for a tension-controlled beam is 0.9. This is the desired failure mode, where the steel yields before the concrete crushes, providing a ductile failure. FE problems are almost always set up to be tension-controlled, so the design strength is 0.9 times 3,202, which is 2,882 kip-inches. Watch for a final trap, the required units for the answer. If the exam wants kip-ft, you must divide by 12, giving approximately 240 kip-ft. Another common mistake is using the beam's total height, h, instead of the effective depth, d, so be careful to use the distance to the centroid of the steel. To keep this process straight during the exam, remember the phrase, calculate tension, solve for A, find the moment. This stands for set compression equal to tension, solve for the stress block depth, A, and then find the moment using the moment arm, d minus a over 2. This simple sequence will guide you through the problem every time. For free practice questions, AI-powered explanations, and more exam prep tools, visit openexamprep.com. That's openexamprep, all one word, .com.